Get her rolling. So first. So here's a question about the end, so
Because the way we define sense is sense.
if you have a partially word set property that every non-subset has a small cell, but then it totally. You want to quote that or say, we know from, or whatever, and that's fine, right? I'm not gonna, that's not where I'm looking to split hairs. In fact, I like people to take shortcuts, as long as they leave grandma's house, not the woods. Yes.
I have a question on like, there's a term, like if the order A, the order C, and then the order B is order, can we basically use, like, is it A and B? Oh, wait, never mind.
That's essentially what the problem that she's asking us says, right? So what's in this problem is. So did I get that right? Did I get that right?
Please, it's just A, B.
A, B, and C. Well, it doesn't make any difference, right? So we'll flip this way, then show. So now let's see what we're gonna do. Capital. Well, in this case. Given by class, always be easy. What I need to do is start with more pair. This one in A, this one in B. So I'm glad I actually copied that wrong. So let's figure out what it should be. You need to get output C, D. So what's the easiest way to do this? Right, so to get first output in C, is this tool. Little f of A. Get the second coordinate in D, use this tool. So let's see what we've done. We've taken two bijections, put them together to make a big bijection. Right? So what we got to do? Certainly, the way we built this, your input ordered pairs in AB, your output's in CD. Okay with that? So this is a function that goes here to here, just like we said. Built that thing. Let's see one. What we have to do? We need to show that those two inputs, the A comma B and the C comma, I'm sorry, the A1 comma B1 and the A2 comma B2 are the same thing, right? So what does this mean? Well, this means that we're there F A1 F A2 B. So where do we go from here? That's essentially it, right? What does it mean for two ordered pairs to be the same thing? It means the coordinates have to match, right? So. We have what's the next move in this tantalizing game of mathematical chess? Okay, so in particular, what's the important part about the by here? They're one to one, right? So. Things. Roll that. Now we're almost there. So, that A1 and A2 are the same, B1, B2 are the same, we're very the same. So. Now on to. Okay, so what do we have to show? What is our burden? Well, we've got to pick an arbitrary element of the codomain and make sure that it's actually in the range. There's something that goes to it. So here's where we start the ball rolling. We need to find an ordered pair from A across B that goes to it. How are we going to do that?
Back to use the inverse one.
Oh, okay, maybe on what you want to use it though.
Inverse of C should be 70. G inverse of
And when you say F inverse, you mean little f, right?
sure.
Right, because big F is composed of these little,
Yes.
the little f and the little g are the ones that are bijection. You can do that, but here's what we know. C is in C and informated C is onto, right? So, conclusion. Great. Now let's use the ontoness of G. Remember that D and G, D is onto. So what do we know? So what's the pre-image? What's the element we're looking for? It needs to go to C comma D. D comma D, good. One turns on to say F from A cross C cross D.
Constant and are equal and C and D or I guess A and C are equal, B and D are equal. That like the
You don't
process.
mean they're equal, you mean they're.
They're more, yeah, they're cardinalities. So like, and then if like their cardinalities equivalent, then it's bijection. So could we like state that? Like since across,
Well, okay, I see where you're going. I think, so. But no, you can't say that. It is true from this, so her point is this, we know this right here, you get. Now, this is true. Not mean that F there is a bijection.
Okay.
But even if you know that F is 1 to 1, it doesn't mean it's onto, and even if you know it's onto, it doesn't mean it's 1 to 1. That's the problem when you get to infinite sets.
Okay.
Right? So yes, this is true. The way you prove this from this is from that function.
Say we just take that F with that right there. Say, and it's just.
Whichever you talk about, capital.
Well,
Okay.
if we construct a function, with, let's say H, from A to range of X, where H of X equals F of X. Like we say that by nature of construction of function.
All right, so you start with this. So let me write down what you're doing so everybody can share the experiences. So you've got this. So he said, okay, I'm just going to give you a function. And now he wants to build a new function. You might ask, what's the only difference between this and the original one? Is the fact that there's no guarantee that this original function is on. But to speak to the comment you made last, yes, this one will be onto by the way we constructed this. Okay. Everybody, so this H here is on, it's not on the C, it's on the range of F.
So. We want H, just say by nature.
I mean, if I was in a hurry, I might say that, but yeah, so. Here's a quick proof. What does an arbitrary element of the range of A look like? It looks like F of some A. And there you go. So H goes to the set of A. Okay. Other questions?
like in general, if like two sets of arrows disjoint, like why is the intersection like or why is the order of the intersection A intersects B? Oh wait. If they're not they're not going to switch. Like why do you subtract those things?
You subtract the intersection.
Oh, yes. Or like why do you subtract like the opposite of whatever it's do like intersection?
Let's see. Well, let me so if you have just for two sets. They make this work infiniteness too, but you're right. So. So my set here has 10 dots. Ready? I'm gonna call this part D. Purple. Well, think about what you're doing. How many elements are there in A? There's 7. If I agree with this, there's 7 dots in it. Looks like. I would say there's about 6 here. Now, if you count the elements in A and the elements in B, you don't get the number of elements in U, you get too many. And what have you effectively done? When you counted the elements of A and then counted the elements of B, you double counted these elements that were in the overlap, right? And so that's where this bit comes from. When you do this, you will always double count what's in the overlap. So you got to figure out what column. Now, if your sets are disjoint, there's nothing in the overlap, there's no harm done. Because when you subtract out the overlap, you subtract out 0, right? That address what you were.
Yes.
I think I did ask. I'm pretty sure on this exam that every definition I asked you was after first exam. I mean, it was plenty. But so what I mean is you might need some of the results from earlier in the course, all of this stuff. Well, here's a great example. To function in this part of the course, you need to know how to do induction, for example. So, okay. Other questions?
So say we use the axiom choice, and we take something out of set. Is there like a way to reset that choice? Like,
How do you mean reset?
like, let's say I take an A and A.
Yeah.
I want to pick another element today. It doesn't matter if it's the same element or different elements. Like some terminology we can use to say choose by axiom choice, choose another element.
Well, I mean, I don't have to use the active choice to pick an element of this set. That's one time in anything. So, sometimes what's done is, well, I'll give you a good example. One of the theorems we talked about in that section is any infinite set has a denumerable subset. Okay. Well, essentially what you're doing is you're using the axiom of choice to pick countably many infinite elements at a time. So you can use choice to keep picking the set. I think it's what you're asking. Y'all let me know if it gets too hot. Turn that thing back on. Is it cooler outside than it is here? Okay.
Yes.
Well, it can't blow as bad as that. Let me know if it's too hot. I'll plug it for. Yes.
I'll just listen to that. For question 5 of 2019,
Mhm.
I don't need A or B, I just need you to explain the part about the axiom choice. Like, it's asking if you needed it for those groups.
Well, I can't really help you until I sort of done it. I think it might be good for context. So show that it's one function backwards, it's on to. Show that it's on to backwards. Okay. So. Here it's F, A, B. That is this one to one?
F from A to B is a function. So the F is 1 to 1, then we can find the function G from B to A that is one.
And then probably show
The opposite. Right? Just,
if there exists.
F is 1 to 1, then H from B to A. I mean, sorry, F is on to, and a function A from B to A.
Exists, H.
B to A.
Then I'm gonna add you into this, that I have this choice. Okay. Let's look at one first. So I guess if we're not putting on the moment, like right here. Suppose you have F. This there exists function, and this again, it's not from a proof, but I like to draw pictures sometimes just to help me in my thinking. So we have a function from A, B that is 1 to 1. Maybe other dark over here. Okay. We build a function that goes backwards. Well, some of the places are fairly obvious. Let's try to build you. Number one. Element. I'm assuming that A and B are not empty sets, otherwise I don't have too many functions here. So I'm going to pick an element Y and A. 2. Find G of X, or G from B to A. Let's do this.
Not in the range. We have to Y, it's in the range. We take the interest.
I'm gonna let you. The, A. Yeah. So look at my B here. My B might be here, and I say, hey, look. There's an A that goes to it. And I'm gonna let G of B be that A. So basically, I just run the arrow back. What's the first thing I should worry about? Well, so what if this happened? I might be in trouble if this happened. What if B should be this? It can't happen. Why not? Because it's 1 to 1. So we'll get to that in a minute. We'll justify all this. We just run the reverse here. If there's something, I look at my B. If there's something that came to it, that's where G goes. And what if not? What if we've got all these little lonely, sad B's that have nothing going to them? What are we gonna do? Get a big squeegee and dump them all into Y, right? Yeah. There does not exist a such that right. So if there's nothing that goes to it, we just dump it all back into Y. So here's my predetermined Y. So Y had to go somewhere. So this one went back here, but then everything else did too. So they just pile on it back here. Everybody understand how that works? Okay, so let's get real here and prove. Let's suppose I need to show that when we put this as for any input to G. Right. So let's suppose let's take our input here. I want to show that there's one and only one out, right? Yeah. E equals capital A, son. Then it's A. And why is that? That's right. Suppose A1, A2, and A are such that F of A1 equals suppose both A1 and A2 go to B. Well, what do we know about F? It's 1 to 1. So So, first case, if there exists an A such that F of A equals B, then there's only one place for it to go, so the output is unique. That is to say, G is. This very heavily depends on one, and the rest of it's going to be each. In the second case, there doesn't exist A such that then we have a unique output. So there's no ambiguity, right? You could do this in terms of relations if you like, but I think this is good. Oh. And is this function also? Certain, because we jumped everything up, so. Okay, so we need to find something in G that, something B, the G takes to A. What is that? How do we figure out? So remember, we're trying to show it's onto. So we need to show, remember, G is going from B to A. We pick an A here. How do we show there's something in B that G plats over to this A? How about that? So G of F of A, read the rule. We're plugging in F of A for B. Well, look at that. A is equal, or A is such that F of A goes to B because this is back to A. If you look back here, you can see it from the picture, right? Even though this is a primitive picture. Notice we dumped all that extra stuff onto Y, right? But it didn't matter because everything in here is covered by its reverse arrow. And that's exactly what happened here. We started with something in A. We sent, that's the arrow going that way to F of A. And then G sends it back to where it started. Everybody okay with that? Yes.
I have a question about like the issue of function part. So I know like the well-defined like that they can't equal two things and stuff, but like by the definition of like function, like how do we show that the domain is precisely?
Oh, okay.
Or like what does that mean? Like I know what the second part of function is, but like what is?
See this dumping we did? That's what we did to make sure the domain was all big.
Oh, okay.
Because we knew where to send these guys, so we're at the head of the arrows. And then we had all these roads, maybe weren't there. We dumped them all there. So that's a good question. It's a really good question. That's what we did to make the domain all.
Oh, do we have to make a statement about that or no?
Well, I guess if I told you to, I'd be a bit of a hypocrite. But that's what being a teacher is all about. You should probably say something. For perfect results. Do we use choice here? Well, we didn't make a choice. Let me rephrase. did we use the axiom of choice, or did we have to use the axiom of choice? What choices did we make along the way? All right, this was really the choice we made, right? Selecting this purple white, don't everything, right? But you don't really have to use choice with that, because what do we have? We have a non-empty set A, and we can choose an element out of it. Choice really comes in when you have to make infinitely many choices altogether. If you're choosing out of a finite collection of sets, you really don't have to use the axiom of choice. It's only when you have infinite sets. You'll see something that's a little more dramatic in a second.
Wait, how do we know that this isn't like? Well, or like, how do we know that this is finite?
Because I didn't say A was a finite set. I just said, it's a finite number of sets, just A. And all we had to do, here's what I knew about A, because I picked that purple Y. A is a set, it's not empty. There exists an element in that set.
Okay.
So there you go.
Okay.
But number two, I think
Can you re-explain that? Sorry. The part about the axiom of choice, like the difference between it being, like, if A is, say A was, infinite set, so B.
it doesn't matter it doesn't matter whether A is an infinite set or not. Right? It is a set.
Right.
It's not empty.
Right.
What does that mean? There exists an element in it.
Right.
So you can pick an element out of it. Now, if I said, here's an infinite collection of sets, I want you to walk through and pick a cookie out of each cookie jar. That's where you need to, if you need to make these need to make these choices all at the same time, right? That's so. We had this result earlier. If A is an infinite set, then it contains a enumerable set. Seems to be very obvious, right? I think, because here's the way this works. Now, what we did previously, and thinking this person here, is I had a set. I don't care what's infinite or finite, it's not empty. And so I picked a single element out of it, which I can do. How do you prove this? Well, start with A. A is independent, it's not empty. So here's what I'm gonna do. I'm gonna pick X1 out of A. This makes my set smaller. But it's still empty. You can argue that because if it's not, then this would have been fine. So out of this one, 1 times 2, I can pick an element. This makes the set smaller. Out of this, I can pick X3. And I can continue this process, right? At any finite stage, you don't need the axiom of choice. You can just do this. You can do this twice, do this 100,000 times. You don't need choice. But to do this infinitely often, to get your denumerable set, you actually do need the axiom of choice, because what you're doing is you're making infinitely many choices, right? And yes, when you make it one at a time, it seems, when you make it a finite number of choices, it seems, well, it's obvious I can do that. Can you do that forever? Right? Can you make all those choices? Because to extract the denumerable set that we're extracting, at stage 1, is that set denumerable? No, it's fine. It's countable, but it's not denumerable. At stage 2, now it's a bundle of two. Right? At stage 3, it's a bundle of 3. Right? At the stage n, it'll be x1 up to xn, right? What stage do I have my denumerable set? I never have, right? Not in a finite number of stages, right? But that's what the axiom of choice says. I can make all these choices forever, and axiom of choice, big smile, I get the denumerable set. It's subtle, but you can do this any finite number of times, but you need a little bit of extra gas to get that entire denumerable set extracted. Does that make it a little better? But it's still a little bit painful. You should feel a little pain.
So this only applies to infinite.
Yes, so if I've got the set of people at the table, I can go through and pick you and you and you. I don't need anything mathematically deep to make choices from a finite number of non-empty sets. And in fact, one of the things the axiom of choice is. So let me give you another example of where choice comes up. Suppose A is A, B, C. And set N, well, I'll call it N, so numbers is going to. Cartesian product empty? No, prove it. And all you gotta do to prove it is just tell me something that's in it. What's in the Cartesian product? Give me anything. Okay, sure. A1 is an element of this. So this is not it. An equivalent statement of the axiom of choice is any Cartesian product of sets is of non-empty sets is non-empty. How did I make this choice? You all made it for me. You said, oh, I'll take A from here. You know, use window shop. I'll take the A here and I'll take the 1 here. Right? If I've got infinitely many sets, how do you make that choice all at once? Right. So one of the equivalent conditions of the axiom of choice is if you have any product of sets, not just finite, but infinite, then if you have a product of non-empty sets, it's non-empty. Now, out of each one of those individual sets, you can pick an element. Any of them. If I just say, even though I've got an infinite list, I can give you one. Here's one of them. You say, oh, I like this element. I give you another one. Oh, I like this element. But can you pick something out of it all at the same time? Because you have to pick things. And that is, it's a subtlety, but it's actually important. In fact, if you don't have the axiom of choice, there are models of set theory where there are infinite sets that do not contain two subsets, which is we don't play in that playground. You have to be like, you know, in a rubber room with a bunch of magicians, but it's out there, so you have to be careful about it.
So like the infinite set of reals is what's a denumerable subset?
Oh,
Like it's
the
0,
natural
1
numbers,
is
for example,
Oh, okay.
or the rationals. Okay.
So axiom of choice is redundant for finite sets, but by using it, it gives us like the legal room just in case the sets are.
Yeah, right. So there's no harm in using the axiom of choice to go through and pick this, right? Except you'll make people that have constructed this really angry at you. It's like this, right?
So in part C, we said that one we did use axiom of choice.
Well,
that
let's finish. Let's do 2, right? Because in the first one we didn't really. We made one choice to pick that Y, but that was picking some element out of a single non-empty set, right? Let's look at 2. Show if there's a function A to B that's onto. then there exists what we call H, D, A, that, you know. Okay. Let me try the picture again, just to kind of give myself in here. You're fine. Let's see if we can figure out what we do. I want to find, so the orange lines are found on F, and I want to get H to go backwards. That's right. I can't just flip the arrows like I did last time, right? Because then I'll be in Jim's world of pain, right? Because if you flip the arrows, what happens? Is that my picture here is still under a function. So what do we have to do? We have to choose. Right. Here, well, there's no doubt where I want this one to go. But here with this fellow right here, I need to pick one. Maybe that. And with this one, maybe I have to pick one. Because if I pick more than one, it's not a function. Notice, just in this little model that I've drawn, look at the purple function H that goes back. Does everybody agree it's 1-to-1? But it's not onto it, is it? Okay. So how we're gonna, I want to make something concrete. I want to make a definition of this function that goes back. How can I do that? They choose, right? So maybe that's something that we need to do, because I mean, I just wrote this function down, but there's some variants I can do, right? Doing this procedure the way I do, this thing has to go back here if I do this procedure, right? But this has 1, 2, 3 choices, and this other one has 2 choices, right? So I guess if I wanted to if I made different choices, I'd still have 6 functions, but they'd all be 1-to-1. It's just, the question is, where does the arrowhead go here, and where does it go here? Everybody agree with that? So, we point out, since F is onto for all E and B, I'm gonna come here to where this thing just overrid me. Like that. But this is the pre-image of B. Since F is onto, what do you say about that pre-image? It's not empty. Everything has a pre-image. No matter what I pick over here in B, there's stuff over here that goes to it. Here it's scanned, but for this one it's pre-images here. And in fact, there's no reason to suspect that a pre-image of some point might not be infinite, right? I just too lazy writing points up here. This is non-infinite. I think that's what you're doing. So here's two back. Here's the X. For all B, we select. There we go, made that choice. We call it A. And inverse. Now, I'll flat tell you that this probably requires the X choice. It won't in my picture because there's only finitely many B's. However, if the codomain B has infinitely many things, then there'll be infinitely many of these preemptive sets. So you'll have to make infinitely many choices. But simultaneously, right? Now, fine. I'm gonna increase this notation so that you know that this is the A that goes into B. So what this means is F of A sub B. That's right. So where does H and B go? And this is exactly what we've done. But what did I do before I defined that? Before I defined that function, I went through every single one of these points, which is pre-image, and I made a choice. Okay. And actually, I might be making many columns of them choices. So definitely use the expert choice here. Okay, let's finish this off and verify this works. Um, Right, so this is a well-defined function, right? Because your input is B, your output is sum. And we've chosen only one, A, so B in this. Let me point out. X. F inverse. B. Intersect. F inverse. B prime. If B. Is that clear to you all? Yes.
What if you're, so what if you set B, what if your second is two points B? You only choose one A.
So where this, do you have a picture in your head that you can draw for me?
I mean, not really, like, so if you have, cause you're looking at, you know. You're looking at the set of B. But if you have two different B's in there, you do this.
Ah, okay, so suppose you have two different B's, right? I find the intersection of these two sets is empty. If you have two different B's, there's no overlap here. And I will prove that. So What does this mean? This means that f of a is equal to b, and since it's in here, f of a is equal to b prime. What is f? It's a function. So b. So if these things have a non-empty intersection, this can't happen. So there's that's why this is a unique choice. We look at every pre-image and we choose A sub B, and there's only one. Well, if might feel like choose, but you never have to worry about this being in the pre-image of anything. That makes G, or I'm sorry, makes H a function. Now I claim that H is 1-to-1. Suppose H B equals H of B prime. This means using our notation, A sub B is A sub B. Right. Which means what like what this by definition is B, and this is B. So H is done. This one basically, this one uses choice. Be careful about this. Let me recall for you. If you have a function that goes from one set to the other, so we've got something like this. Um, suppose it have it's a subset. So now inverse X. A lot of people that's the inverse. That's not what this means. You gotta be careful. It can mean two things. This means the pre-image, right? Yes, F inverse means the inverse. If F is a bijective function, and this goes from the codomain of F into the domain of F. But here, under this notation, this means pre-image. This is all the A and A that ends up in S. So for example, So. It's the empty set. By definition of the function from A to B, everything in A goes into B. Now, what if I took these 3 points? Let me see if I can draw this. I have my balance. We'll see. All the stuff that goes back. This. And. This. This. These 3. And, it's like all of those. These 2. This one. This one. So all the stuff that's in that blue circle is F inverse. If I let this point be B, then F inverse B, in this case, I'll use when you see the symbol here, you don't mean the inverse function. What you mean is all the stuff that happens to go to this set. In this case, the set is just a C.
Back to the other function. Of like eight. So like it's a function because like we're choosing one eight to be to equal.
Right. For any input B, like what you did is you picked one and only one element of F
like
inverse.
that, go to it.
That's
And
right.
then so how do you like state? Because like if we write just like A sub B, like are there multiple A sub B? So how do we know that it's only that one?
Okay.
Or
So
like by the fact
let's do that part of it. Here, now that I want to prove this, so. That's really the basically. So, the first thing I want to do, let's go through this plan. A prime if leave what was then, then what I'm saying is, so Sophie's point is, okay, I go through every one of these B's and I pull some A that goes to it. How do I know that I might not, there might be an AB that's in 2 of these different, right? So I might accidentally make a not function by, picking 2 different ones. Right? Well, and actually. Actually. My statement here is true, that doesn't really matter, it'll be a function of nouns, but let me finish this up here. And also. Uh. But it's function. So, there's two of these preempts can't have any overlap. But it doesn't matter, because what happens is. Given this B here. There's a unique ace B. That corresponds to B, because that's what we pre-selected. Remember how I said, okay, we're gonna go through every B and B, and we're gonna pick a unique one of these. That sort of makes it a function, because any input B, who's this unique selected A, B, it's an out. Is that better? Oh, in zero. Okay, so does that make sense?
Yes. So. For the first one, since we only chose like a single element of A, like we weren't really making it like we just like that one element. And like, so it didn't matter. Got it. And then for this one, like since B can be infinite and A kind of choose.
Well, that's right. If B is infinite, then you're choosing that out of every F inverse of B, right? If this list is an infinite list, then you're likely not to get, you're gonna have to at least use calculus.
Oh.
Right? Everybody okay with that? And did I get you, Alice? Okay. Yeah, well, do your best, write down the details, but I do tend to give you all flat on the exams. Yeah, but you'll need to, yeah, so I'm saying these class today, like those poker problems. If you write, oh, the number of things I need is 13, choose one, 6, choose two, leave it like that, I'm okay with it, right? If you want to calculate it, sure. Yeah, you need to calculate.
I've seen this on like multiple exams. So this is question 3. Show that a relation R on A is like one to N. Like,
If and only if it's, yeah, it's right.
yeah, the identity. I'm just like, I'm just confused on like so that would be just do symmetric.
It's if and only if, right?
Yes.
This is a good one to go over kind of definitions. Let's go through this. So the question is, the problem is show. What do we call R full explanation? relation. Are
Function. Or like,
oh, I'm sorry.
oh,
Isn't, I think this was.
I think you're gonna go on a.
Okay. Now, recall. That's it. All four pairs of double line. Okay, so let's go through this. Which way we go first? This way? This way, right? Suppose R is equivalence relation. So, let's let, well, actually, it's not for my printer, but I'm gonna recall. That's. Let's say two AB R files. Three different differences. Four and five. That's. And function. Domain. Or is. All day. What's the second?
Correct.
That should be done. Okay, so the request to go left to right here. What we do is you have all this garbage here that relations. That. So. What can we? Very good. But I just told them here like this. Right off the bat, with the fact that I've got, reflexivity. I. On the other hand. Show that's. How would we do that?
X that relates to X from the equivalence definition. We know that and X relates to Y minus the X.
Say, like, let me say, symmetry. Y axis and R as well. Okay, so how does that help us? I think we skip the step now with the budget come up. Also. Why? Well, that means X is an A, and we know from the fact that the square function must have X axis. Since X, X, must be clear. X is Y. I can see this business right here, function. Therefore, it's Y equals X X. So. An arbitrary element parts contained in that. So. We've shown the forward direction, and we've shown it's a forward relation and a function. And notice, really, what did we have to use? Well, all we really had to use, I think, was reflexivity and this part of the function. Right? So that was nice. Well, how about the other way? I think the other thing actually be easy. RC identity relation. Everybody got what they need here? This is just a matter of properties. It's also symmetric because all the pairs are equal coordinates, right? And in a very silly way, it's translated. Because the only way you match the stations, the only transit relations, AA plus AA. Domain of R is equal to A, because everything goes here. And A X equals X basically verify that the identity relation is both, equivalence relation and its function.
It's just like. I thought sort of like. It's defined that like A is less than B. So like, since it was defined that A was less than B, it wasn't like symmetric, you can switch. B
Yeah,
and
that's
A.
right.
But like, because like A is equal to A, you can't switch, like, since they're.
Well, so it's the difference in partial order. Versus equivalence. This is why this mimics E. Right? One, A related to A. Well, flexing. Symmetric. And transient. That's what it is for partial ordering. So for both equivalence relations and partial orders, you have reflexivity and transitivity. This mimics equals and this mimics less than or equal to. Because if A equals B, then B equals A. And this one is if A is less than or equal to B, and B is less than or equal to A, B and A are the same. And that one's called anti-symmetry. Or the anti-symmetry. Yeah, and actually, I think the same problem is true. If you replace, we have the function, but if you replace function with partial ordering, the way I wrote it down the first mistake, because you have to have all four of these properties, right? And notice this one right here, if AB is an R and BA is an R, but AB comma BA plus A B, that means that means it has to be, and that has to be with A and B the same thing.
Like, other than like that, like A, base, all those. Like, how is time symmetrical?
How is it?
Like, because we said time was an equivalence relation. Because like you can have like a different day, but the same time.
Oh, okay, so you're thinking sort of modular. Okay, so, right, so you might say, uh, um, I don't even, I assume that this is like the real numbers. And I guess, I don't know, how far back and forth, but I'm declaring. On set, I'm declaring. One, Whatever. Teaching like, later. Yeah. So in other words, exact stroke of noon on any day, that's all equivalent. Now, I'm idealizing this problem. I don't want to get up here in arguments about the Earth's rotation slowing down or leap years or any of that. I'm just going to pretend. Right? But I'm going to say that 2 times are equivalent if they vary. The difference is exactly 24. How many equivalence classes are there? Actually, men. And again, I'm going to this physical argument here, but if we measure time continuously, right? So 12 minutes plus any real number of time. So they're equally many seconds. Yeah.
Just to talk about, I did, what is it, A?
Oh, this should be an A. That's a track. Yeah, that's a type. This. Say. Where I am going to do the hour. This. Oh, but second, exactly. One. So if your time is exactly midnight, you're in the 12 o'clock hour. If it's 11:59, 8, you're in the 11 o'clock hour. How many of them? This should be in the bonus class because anything, if you have the exact same time, it should probably say that. Right? Do you all have anything that you need to ask before you?
No, I was, yeah. Thank you so much.
Sure. Notice that if T1 and T2 fall in the same hour of the day, so do T2 and T1. And T1 and T2 fall in the same interval, and T2 and T3 fall in the same interval, and T3 fall in the same. How many equivalence classes are there now? Right, 20. Because you've got anything from midnight to the next. Well, I'm assuming that we're on military time, standard T, right? If if the AM PM, but 12 o'clock, then it'd be 12 classes. Okay, any questions?
So if f is a function of a,
Which one? It's 6.
yes. So is that just a bijection from?
Sounds subsets of action. Okay, so let's. My, well, were there any adjectives attached to this, or these just functions?
Just functions.
How would you show this? What do you think? I mean, this is like sets, right? So. Just need to show continue both ways. So let's start this, let's let. Let's show that the left is contained in the right. So let's let y be in left. That's cool. It's not gonna be a hard problem. We're at the hardest part. We gotta try to deconstruct what the heck is this saying. What does it mean? It's looking for y to live and f of the union that you call it. So we break it down to the piece of what we're going to do. This means y is f of c. Right? Y is f of something. What can I say about the something? It lives here. Period. What does this mean? What does it mean for C to live in a union of a bunch of states? It means there exists some I or C lives in. There exists J and I such that C lives in S and J. So it's got to live in one of these. Right? And take people. So what does this mean? So if C lives in SJ, you take a look at overhead and see how to push this further down the road. F of D lives in F of SJ. I don't know much, but I know that this means this lives in the union of all. So my Y, which is F of Z, lives in one of these things, so it lives in the union of all of those things, right? Does that make sense? Okay, we totally conquered that. Right, we need to show the other one. Now suppose of all. What does that mean? That'd be one of them. There exists J in my index setting such that Y is in F of S J. We agree on that? Let's see, who's this one? We all agree with that, because actually SJ is one of these. So some kind of weird. How does it spell it? This is small, but this is an F of this thing, it's certainly an F of the bigger thing. So. So, we got both contained, so, got it.
Yes. Slight unrelated but application question. This problem would this mean we use the axiom of choice to say that there's a non-empty subset of SJ, in fact that we were assuming there was non-empty.
I don't think we use choice in this, actually. Because. This is all just kind of by definition. I mean, we're not making a choice, for example. We know that Y is in here, so it's equal to something. And that something has to belong to you. So by definition, this has to be in one of these little SJs. We didn't make a choice in certain sense it's thrust upon us. Here, yeah, so we start here. So here exists some J. So once again, this just has to be something in the beginning. And so, yeah, there's no need for choice here. Yeah, but that's an easy disease to suffer from, and I've been doing it for a long time. So you start thinking about the action of choice, and then you start thinking you see it everywhere, right? And it's in some sneaky places, that's for sure. Even in some standard textbooks, graduate textbooks, there are mistakes where, well, I wouldn't really call them a mistake because in my research area, we kind of freely use the action of choice. But I think sometimes it's good to point out where choice is made. There's a lot of books that just kind of do things without saying the choice or not. Any other questions? Yes.
Homework question, homework 10, question 2, and homework 7, also question 2, deal with that relation, where F1 minus F2 is continuous, that it's under.
Yeah, or whether it's different.
Yeah, could you go over kind of all of that?
Okay, so
I can read out any of the questions.
I can probably cover a lot of what I asked, just, and if I miss anything, you can let me know. So what we do is, we start off with all. I've got no idea, anyone can call it everything. This can be incredibly messy. Right, there's all kinds of functions that are not things anywhere. Can be just a wild mess, right? What I can do is, I can, here's the equivalence relation here. Say F one is C equivalent F two, if F one minus F two is continuous. Got this. Say the two functions are equivalent under D. Yep. F one minus F two is differential. And I asked a bunch of questions about equivalence classes. So continuous implies differentiable, or differentiable implies continuous? This is tight. It takes more for these two to be put here than it does here. So if F1 is and F2 are D equivalent, this implies F1 and F2 are C. Because the difference is differentiable means the difference is continuous. You okay with that? You want me to show that these things, either one of them are equivalent to one? You comfortable with that? Sure. Let's try this. In function, F minus F is 0. This is what I'm saying. That's not a word. If F 1, then F1 minus F2 is continuous. So F1. So how do you get from here to here? Just multiply by negative. By any scale, any multiple of continuous functions continuous. Notice this is also true if you replace the words continuous with differential. Right. And finally, one, two, three, implies F1 minus F2 is continuous. And F2 is F3 is continuous. Now, you remember that we add two continuous functions, you get differential. Absolutely. We add two continuous functions, you get differential. So Notice that we're in here. Place one. See. Till the is also. So. Let's see. Oh. So, this. This function can be everything. So I think there's some people made the mistake of thinking, oh, that means f is continuous. No, it doesn't. It just means it's the equivalence class. Right? So, what do you do? Suppose I have. We can do an example of a function that is. Notice that. In fact, I can describe pretty nicely what the equivalence class is. The equivalence class of this function is this function plus any continuous function added to it. That's the collection of all that. Here's one. F is in there, you add 0. F plus 1 is in there, F plus 2, F plus 3, F plus sin x, F plus cosine x, F plus absolute value of x. This equivalence class actually makes less. This is a smaller plug. Notice this one is excluded from this club. Because the difference between f and f plus absolute value of x is absolute value of x, which is continuous, not in this club. So these equivalence classes are smaller, they're more exclusive clubs. So that's kind of what this is all about. And it's worse. What does this equivalence class look like? It looks like f plus any differential function. Right? So you can throw out all the ones that are continuous but not differentiable, right? And that's your kind of small one. So we have things like, so this is a smaller equivalence class, so there's probably more of them. Right?
why the question, it's smaller.
Remember what equivalence class does? It divides things up into, it partitions the set. So if this is not a set of all functions, then maybe this is the equivalence class. And actually, like, proving your homeworks. Well, smaller, more exclusive part you get into. So there's more of, because you're still partitioning the original set. Now you're just, these are smaller pieces. So that's the rationale. So, can't remember from homework, but there should be an on-to math here to here. Does that sound familiar to homework problem? And how should this work? Well, here's an equivalent. So these little boxes are all the equivalence classes underneath. Right? Let's say equivalence class of a function. Let me call this medicine. Let me call this capital. Got to come up with an equivalence class of continuity. Remember, it's math. So what's the easiest thing to do? Xerox that student. Because here, F, maybe F is here. This little box right here is this equivalence class mod D. But the whole orange triangle is equivalent to class of C. And so notice, I don't expect this to be onto because maybe there's a G over here. And an H here. These are two different equivalence classes under differentiability, but they'll be the same equivalence class because they're in the same big orange piece of paper. The other. Let's prove that this works. What's the first thing that I have to do? Good. We have to show that this is actually a function. What's the potential hazard here? In any of these equivalence classes, I hope I've convinced you that there's infinitely many functions, right? So here's what happened. I might innocently say, hey, you know what? I'm gonna have F represented. And just as innocently, she might say, you know, I like F plus sine X, right? So we might, no fault of our own, pick different representatives. I pick F, she picks F plus sine X. It's another function in there. It's perfectly good. We do this to it. I do bracket F C. She does bracket F. She does bracket F plus sine X with C. If we get different answers, this is not a function because we put in the same input, because of the same equivalence class. We get different outputs. It's not right. So let's show that this is well defined. So let's suppose that the equivalence class of F under D is the equivalence class of G under D. Right? This is B. What does that mean about the relationship F and G? It means their difference is differential. Which implies it's Did somebody read my mind and say the next words that can come out of my mouth? Continuous, good. Differentiable. What perceives the difference between continuous? It's that F C is same thing as G. Great. Which means capital F of F is capital F G. So in other words, when she put in her representative and I put mine, we have the same outcome. So this is a function. Yes.
So like, for this, like, the equivalence class F under C, like, it's the same thing as the equivalence class aside. Under C.
No, it's the equivalence class of F plus psi. Right, because if the equivalence class of F under C is the equivalence class of sin X, this would mean F minus sin X is continuous. And I have no evidence of that. I mean, it could be, but F minus sin X would be continuous, that would mean that F has to be continuous. And if I start off with this particular function here, the answer is the equivalence class of FC is not equivalence class. But it is the equivalence class of F plus sin X, because this that is confused because the F's dropped out. But it sounds like a cheat, but that's essentially all there is to it. Okay, everybody okay so far? That mess over there is a function. Now that you know it's a function, that's the hard part. The onto part is easy. Any element of ED looks like this. Anybody see something that comes from? That's all you gotta do. We already know it's a function. Just find me a preamble. So it goes to that. Oh, yeah. Like crazy. That's what this. I've got this going. Let's try this. Suppose C. Say first place, we need to find F of blank. F C. Whatever function it is, doesn't matter. Now, this actually might be different. We could different represents. Okay, so let me illustrate what happened. Let's say F is in this equivalence class. This absolute value of X. Their difference, the difference between these two is continuous, right? So they're the same orange piece of pie. But their difference is not differentiable. So they're in different blocks. Right? So if I take F, then I'll key on this block. This is the one that goes to the orange piece of pie. If you say F plus absolute value of X, you'll have a different block, but it will still go, it's still in the orange piece.
Like the representative for class of F plus absolute value of X, like if that was the representative, it would be that F plus absolute value of X.
Yeah, that's right. So this is the function F, and the stuff in here, I can tell you exactly what's in here in the box with F. What's in the box with F is f plus any differentiable function. F plus sine x is in here, f plus x squared is in here, f plus 2 is in here, f plus cosine x over x squared plus 1 is in here, all that. What's in here? F plus absolute value of x plus any differential. F plus absolute value of x plus sine x, blah, 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 right? All of these together are in the orange piece, but they're not the same piece because they're different. There's never going to be differential. In fact, the difference between anything here and anything here, I promise you, will look like absolute value of x plus a differential function. Always. It's kind of funny about rooms because these are actually blocks are huge, right? And if you think the blocks are huge, the number of blocks is bigger because of all the functions out there. I mean, even continuous functions are small. So
So, like, if you drew the of F under D and then G under D, like, what would they be the same? I know they'd be the same equivalence block, or like,
if F and G are equivalent under continuity, they're going to be in the same slot. Pizza slice, pizza slice.
so
If they're in the same differentiability block, they will be in the same square. Now notice that any two functions that are in the same little square are in the same piece of pie, but not vice versa. You can have something here and something here. They're in the same piece of pie, but not in the same substance.
So since those are in the same differentiable square, you can, like, you can interchange, like, replace F and G with F, because it's just a representative from that square.
Right, so what we're doing here is showing that it's well defined, right? So suppose you and I pick functions that differ by differential. Right, so I pick F, you pick F plus sine x, pick by differential. You notice their difference is sine x, which is differential. So we say, hey, the difference is continuous, right? That means that we actually pulled, since we pulled out the same little box, we pulled out the same slice of pizza. So the output, it doesn't matter which one, whether we think we represent mine, the output is in the same orange slice of pizza.
So like, when you had F plus sine x there, that was a function.
Mhm.
Like that itself was a function.
That itself
Yeah,
is.
okay. Say it out.
Oh,
Like,
billion group?
I know what the definition is, but like, how do you do that, like, what do you do?
I'll give you one more problem. Yeah, what it means for a group to be billion, so you remember what a group is, right? Got a way to combine the two elements such that they're still in the group. That way is associative. There's an identity and an inverse from it, right? What I don't say is combining the elements, order might matter. Like if you're multiplying matrices, for example. An abelian group is one where order does matter. I'm sorry, take that back. Or an abelian group is one where order doesn't matter. That is, x times y, y times x, same thing. Yeah.
And also, for the second question, like, that is for every single element of the group, like every element of the group has an identity.
No, there is only one identity. In fact, we proved a couple classes ago that the identity is in fact unique. There's only one identity. But what the identity does is it operates on every other element of the group and leaves it alone.
Oh,
Right.
okay.
So think of, if you look at the non-zero rationals under multiplication, think of one. Right? If you think of 2 by 2 invertible matrices, think of the identity matrix.
Okay.
Right? If you think of adding, think of zero.
And then, so inverse, is that one also one, or that one's?
Given any element, every element has an inverse, and that inverse is unique.
To that one.
That's right.
Okay, so there's multiple inverses.
Right,
like
so
one.
if I walk up to you on the street and give you x, it's got a unique inverse x inverse. An x inverse has a unique inverse, and it's called x. That's the parallel.
And then, but then, like, the identity would be X times one, which is the same identity as
Or the
Y.
identity actually is its own inverse. What can you multiply the identity by the identity? The identity actually is its own inverse. And sometimes in some groups, you have an element that, in fact, there are infinite groups where every element is its own inverse. And it's your infection.
Question on like, how earlier we talked about the straights and stuff for like over. I'm still kind of confused, like, I know you have to, like, there are four suits, and then since we're five possible arrangements, it's like four times four, so like five times. But like, why would you not do like, why are you multiplying four multiple times? Like, why are you not doing four choose? Oh, four choose one is just four.
Yeah, that's right.
Oh. Never mind. Okay, yeah, never mind. And then what's his step five? I'll think about that all day. Yeah. Yeah, I look at it.
That was easy.
Have one like every day, like every week, every Wednesday. You're like, I have an exam after this.
I hate ECE. I really like, that is just the one thing that she really likes.
And you don't forget I'm recording with this class, so I can now blackmail.
Oh, please, yeah, please don't. You know, once you turn the recording off, I have a comment about this. Sorry.
You know, I mean, different majors suffer different ways, right? I mean, math majors, I don't think math majors probably, certainly the sciences majors that have the least amount of units, you know, as far as the number of credits, but there's a reason. And engineer takes certain stuff, it's like, thank you, sir, might have another, right? You have to just get piled on that. Yeah, in fact, I know some, I've seen engineering departments where they try to pull what I would call borderline shenanigans. I'm not gonna call it the borderline shenanigans, the kind of, they play kind of shell games with they try to convince you that, oh yeah, I mean, get the target.
Oh, yeah. It's not that, they don't do that as bad here. But I know exactly what you're talking
Right.
Oh, I feel like that's on. Okay, so this is. If I were. What's a. This is. I'm looking at question two. So I'm thinking like, oh, you would just do a contradiction, right? Like show that it's like. Not unique. Or like suppose it's not unique. But like, wait, I'm confused. How do you set up a contradiction? Like, how do you set up?
You go to post set, you go to subset, show them the pass maximum. This maximum. Okay, so. This is not too bad because it's a matter of kind of sort of French definitions.
It's on. 2017. Yeah.
Y'all gone all the way back.
Well, a lot of the questions are like kind of the same. Like there are a lot of like overlapping-ish questions, so I'm just like going to the ones that are like different, really good. And then all the definitions are like there's only so many. So it's like at least half of them are like
So
yeah,
this is
not
basically the question. So you have a partially ordered set, and you find that it's got a maximum element in it. Show that it's unique, so it's in. So.
Smaller.
Well,
So what would be a maximum? What does that mean? Well, I've already given away a right. A supremum only needs to be an A, but for B has a maximum, but it has to be in B. This is maximum and what is it, what is maximum? Say. B is in there and it's bigger than 40. So suppose X is another maximum element. What is the- what is greater than or equal to C, all C, D. This includes D. That is X is greater than B. But as B is maximal. And X is in B, so we really needed X to be B. Must be the case that B is less than or greater than X. What happens on the partial order when these two things happen? I do. The properties that are described. What we've shown is there's a maximum will be any other maximum element equals B. And so there's
so like. How would you do a contradiction? Like, I don't know, like, I've done contradictions on the board, but it's just like,
I
it
would
was
say,
like, I just don't know how to set it up without it being like, not.
well, you could have turned this into a contradiction in the following way. So let X, change that first line to let X be another maximal element that's not equal to B.
Oh, okay.
And then you get a contradiction that way, but you're making your road mess here. You don't.
Like, on the homework, when we do contradictions for like one-on-one and stuff, that's like, to throw out cases and like,
Yeah, you know what, I mean, it's sometimes, some situations, I mean, if you want to prove that something doesn't exist, et cetera, it's kind of an actual, you know. Hey, do what you gotta do.
I have my last question before I get to it. This is from, this is spring 2018. Question 5, it says, give explicitly or clearly demonstrate how to construct a bijection from rationals to the rationals, like without zero. Or explain why this can't be done. I would assume this has to be done.
Yeah.
Just because.
They're same size set.
Can you do, like, would you do? Kind of how you do this.
So you need to avoid zero, right?
So move everything up by 1 pretty much.
So for F(x) equal, I'm gonna move 0 to 1, so 1 to 2, so I'm gonna F(x) equal X1, you know, X. And here, I mean, Or yeah, anything else. So, right, this case 0, 1. Right? Notice, well, let me be clear. You could also make an argument that these are both numerable competitive, including. But it's not like human sacrifice. Oh, is it?
What?
One of those things.
So they probably are sacrifices.
Is it?
I keep hearing like periodic, like.
Do you not hear it?
screaming.
I
No,
guess
I
you're
hear it, but I thought y'all knew what it was.
I'm just. Right, that'd be a good question.
So I'll be careful. Suppose.
Are you sure?
There's just a project.
Oh,
Okay, so let's go that section. Case 1. Solid exhaustive. X and Y both in. See. So that is the both using. So. Fx left Y implies X plus 1. Y plus 1. Let's be check.
Assume the other way is just has to do with that. So.
X, Y, not in. Fx, Y. The only thing I have to worry about now is the next case. Case 3. In 0, Y not in 0. Alright. But technically it's 4 case for versus 2, but yeah, it's slightly. So in this case, f of x plus y implies x plus 1. And so this means, since x is in 0, y is in 0, which is a contradiction. So this case can't happen at all. Because if x is a natural number of 0, then that's. So, because gets x equal y, gets x equal y, and this just like can't happen. Now, on to. Oh. On to. Whatever. 6. C is an actual number. Note that C minus 1, an actual number for 0. Right. And C L. Got it. Case 2. C is not. Then notice that then no. There's one thing. Then yeah, See. It's not numbers. And. C is not zero, so you can see that Q minus Q. So I don't have to worry about that. There's one thing that I really should have done in the first place, and that is show that this actually really goes where I say its input is a rational number, its output needs to be a rational number, not zero. But it's impossible for this to ever turn out zero, right? Because the smallest this part can give a value of this one. And this one can never give a value of zero, because the only way for this to get the value of zero is for x to be zero. And that's not possible.
If you were doing the inverse of this, like, would inverse of x just be x minus one and then x?
Yeah, so now you're going from Q minus zero to Q. Right, so I guess what you would do is you would take all the natural numbers and go to x minus one, and everything else would be things.
So, okay.
Makes sense. Oh, they're also down there at William. Maybe it's a impromptu Julius Caesar.
It's a dance.
What is it?
It seems to be like a dance thing.
I thought it was.
And it's just like a bunch of
there.
people hyping up the dancer.
I know it's there.